Hi, I hope everyone is doing well. In this video, we will quickly go over a basic problem where we will find the optimal weights for a client, an elderly lady who wishes to minimize risk. Okay, so we will get this solution through multiple ways so you can sort of compare. But most importantly, we're going to use matrix operations. Now, the amazing part of side of working with matrix operations is that we are going to work with a very simple problem. We only have two possible assets. We can only invest in bonds and stocks in this case, but the exact same approach that we will use with matrix operations, you can use it for a much larger matrix. So you can evaluate 50, 100, 200, 500 assets. Of course, the matrix would have 100 by 100 dimensions, would be much larger, but the actual work is going to be the same. So the first thing is let's look at the values, the data that we are given. We have a bond ETF, and the bond ETF has a variance that is listed here. So we just in the covariance matrix, keep in mind the diagonal terms, these term and this term, those correspond to the variances. This one to the variance of equity, right? And this one to the variance of bonds. The variance of equity, it's 0.0225. These values are completely random, so they are not representative of equity or bonds, but they're just randomly generated. And then this is the variance of bonds, 0.0004. And in the covariance matrix now, the other cells, this one, it's essentially giving us or capturing the covariance. So this is the covariance of bonds and equity. We have it here, 0.0012. And of course, if the covariance of equity and bonds is 0.0012, the covariance of bonds and equity, it's also going to be 0.0012. Covariance, how one return one asset moves with respect to another, whether how they co-move one with respect to the other, then it's going to be the same if we think about equity and bonds or bonds and equity. Okay, now let's complete this matrix. That's going to be really difficult. A matrix of ones is just one and one. It's just a column vector. It's a matrix n by one, n number, the number of assets you have. That's going to be the number of rows, and then one single column, and all of the elements are going to be just ones. Now let's start off by calculating the variance of a hypothetical equal weighted portfolio. So we just give weights that are 50% and then 50%. It's up. The sum of the weights has to be equal to 100. That is an important condition. So means the amount that we are investing, it's fully allocated among the different asset classes that we are evaluating. Okay, so here to get the variance, we can calculate the variance. But before we calculate the variance, just to make these formulas more apparent, easier to follow, let's give this matrix a name. So we're going to call this COV, COV, covariance. Okay, and now we can refer to this matrix simply by typing COV. And now let's name this one W. And let's name this one ones. If anybody's not familiar with this, you just select the cells. In this case, this is a matrix. And you just go up here, top left, and you give the matrix a name. And now it has a name. There we go. Now, variance, we just follow our matrix formula, okay, that we have here. And we multiply weights transpose times covariance times weights. Okay. There are some rules of why we need to transpose because this is a 2 by 1, so we cannot multiply by a 2 by 2. We have to transpose it, so we have 1 by 2, then we can multiply by 2 by 2. You may watch other videos to go over those specific rules, but in this case, let's directly go ahead and complete it here. Excel has a function which is mmult. Unfortunately, mmult only multiplies two matrices at a time. So we will need to multiply three items. We're going to need two mmult. So we have mmult and then we have mmult again. The inner mmult, we are going to multiply these two first, W transpose and covariance. So W transpose is going to be transpose of W. And then we're multiplying in this inner mmult. We're going to multiply the W transpose. We're going to multiply it by covariance right here. If you look at the here to the left, as we have typed COV, now this is directly selecting the covariance matrix we have here. If we had a much larger matrix, it would have selected all the cells, right? So then we close the first mmult, and now this first mmult, once again, it is multiplying these first two items, W transpose and covariance. Now we add a comma, and now we are in the second outer mmult, and we add W again. So now this is multiplying the output of the first mmult with W here. So the output of the first two elements with the third element, and now we have, by doing so, in doing so, we are now multiplying all three elements. And then I will press enter in some computers. Uh, I believe older versions of Excel, you need Control Shift Enter. You need Control Shift and enter. But modern Excel versions, you can just type enter and the mmults are going to work. Standard deviation is the square root of the variance. Anybody wants to confirm if this variance is correct, right? Then we can, and once again, to let's name a few of these cells just to help with that formula, which I'm going to use now. I'm going to call this WE, the weight of equity, WB, weight of bonds. Then I'm going to call this bar E, variance of equity. I'm going to call this bar V, variance of bonds. And then I'm going to call this cov EB, covariance of specifically the covariance, not the covariance matrix, but in this case, the covariance between equity and bonds. Okay, and now we have named all of these. If you recall, given that this is a very simple, only two asset portfolio, it's really simple to uh, work with the uh, commonly used formula for the variance of a two asset portfolio, which is weight of asset A, asset one, in this case, equity, weight of equity times variance of equity plus weight of bonds times variance of bonds plus 2 times weight of equity times weight of bonds times covariance of equity and bonds. Okay, so it was worthwhile naming the cells because it's much easier to follow the formula. Okay, weight. I'm missing, of course, weight of equity should be weight of equity squared. Now that is the formula. I was missing that. Weight of equity squared times the variance of equity plus weight of bonds squared times variance of bonds plus 2 times weight of equity times weight of bonds and covariance of the two. And then if we press enter, we are getting the same number, and therefore we are getting the same standard deviation as well. Once we have the variance here, let's get the optimal weights using solver first. Why? Because then when we use the matrix operation to find the optimal weight, we will already know if we are getting the correct value. So we go to data, solver, and this is already populated here, but let me just walk you through. Set objective, my objective is N10. So here, variance of a portfolio. I'm going to minimize it. Okay, so I can maximize, I can minimize, I can ask Excel to find to find weights such that I end up with a specific value for my objective function. So once again, what I'm doing here is, what is my objective function? I'm looking at the variance. What is it that you want? I want to minimize variance. How are you should the optimizer solver do that? By changing the weights, by changing W. And there is one constraint: you have to invest all. You have to invest 100%. So you have to allocate that 100%. You have to distribute it among all the assets. And then we click on solve, and Excel found a solution. The solution is here. Let's just type that solution here, minus 3.9%, and then 103.9%. And now let's delete. So this is the solution we are getting from solver. Let's keep in mind what solver is doing is essentially iterating all possible over all possible values for the each of those weights, all possible weight combinations. And every single time then it looks at 0% equity, 100% bonds, and then let's look at the variance. 5% equity, 95% bonds, let's look at the variance. 100% equity, 0% bonds, let's look at the variance. Until it after iterating a large number of times, then it will search for the weight combination that ends up giving you the least variance, and then these are the weights. Now we can also use matrix operations to achieve the same objective, and so let's do it. We can get rid of this, and then we can use uh, this lengthy formula. Let me split. Perhaps it's going to be a good thing to split this formula into two parts, the numerator and the denominator. Okay, so the numerator is covariance inverse times ones. Ones is this matrix, covariance is this matrix. So we're going to get the inverse of the covariance matrix, and we will multiply by the ones. Okay, so the way to do it is mmult multiplication. We don't need more than one mmult because we are only focusing on the numerator, so we only need to multiply two things of m inverse of the covariance. So please, Excel, get the inverse of covariance, and then the inverse of covariance we're going to multiply by ones by this matrix, and that's it. And then we end up with two values. These are the values that go up here in the numerator. Now, let me give you a little hint. In the denominator, if you pay attention to this, we're doing essentially the same. We have inverse of sigma times 1, the inverse of the covariance matrix times 1. If we pay attention to these two last elements here in the denominator, and then we're multiplying by this 1 transpose. Multiplying these by the 1 transpose, effectively it's what we are doing here is we're adding up these two values. If we had a larger matrix, we would have more values. Here we only have equity and bonds, so we only have two values. Okay, but the denominator, in short, what we're doing is adding them up. So we can get the denominator either by following this entire expression. We will do that, but that is the same to, okay, let's just add these two. So the numerator gave us two values. The denominator is just adding these two. And then we divide the numerator by the denominator, the numerator by the denominator, and we are getting the weights. So we just split that formula into two little pieces, and we are getting the solution that we had gotten using Excel, the solver, okay, in two steps. So this is the numerator first, right? The yellow cell is the numerator, and then here the denominator it is simply the summation, okay, of these two values that are generated in the numerator. And then when we divide this matrix by this scalar, the numerator by the denominator, we end up getting a matrix, which is essentially the solution to our minimization problem. Okay, so this is the solution right here. Okay, there we go. Now, let's do all at once in a single formula. Okay, and we can do that directly here in weights. So what we can do is equal m mult of m inverse of covariance, comma, once. This is the numerator. And now we will divide that by the denominator, but instead of splitting these and doing this in this intuitive way, let's just use this expression that we already have. Because we have three elements, we will need two m mults, m mult, m mult. So the inner m mult, we're going to multiply one transposed of m inverse of covariance. Okay, so the first one is transpose of once, comma, m inverse of cov. Okay, and then we can close the inner m mult here. And well, this is the denominator. All of this, but now, right now, we're only focusing on two elements, one transpose, inverse of covariance. We're going to multiply those two. The output here, right? The output of the inner m mult, then comma, we're going to multiply by once. We close now the second m mult. So now what we're doing is transpose once, multiply by inverse of covariance, and then multiply by once. And that is the denominator. So once again, this is the denominator. And now we know that the denominator is just the summation of the values produced by the formula in the expression in the numerator. And then this is the most important expression, which is the numerator. Okay, and then we just type enter and we immediately got the formula. So we just need, we can do formula text. We just need this formula and we can get the minimum, the weights that lead us to the minimum possible risk, which we are going to call, this is an important portfolio because this is the global, we usually refer to it as the global minimum variance portfolio. Okay, and that portfolio is intuitive. Some strategies, investment strategies, bet on the GMV portfolio, the global minimum variance portfolio, and some in practice argue that this is actually a portfolio that tends to perform well, but that is one particular strategy, one particular view that deserves well some attention and some further analysis. Now, once we have this, we already calculated with matrix form the variance here, so we don't need to, it's automatically, this is the variance and this is the standard deviation. This is the lowest standard deviation we could get, we could reach if we are investing in a portfolio comprised of these two positions. Okay, now let me give you a little hint, another hint. This expression in matrix form, there is a shorter formula that works only when we have two assets. Okay, and that formula, we can use it sort of to confirm that these weights are correct again. So that formula is variance of asset 2. So I'm going to say bonds minus covariance of equity and bonds. You can write that formula down later on, but that formula would only work. It's simpler, but it only works for a two asset portfolio. And then divided by variance of asset 1 or equity here plus variance of asset 2 bonds here minus 2 times covariance of equity and bonds. Keep in mind the difference when we mention covariance EV here. We are not, this is not COV, the matrix. We are only referring to the specific covariance between the equity and bonds, which is here, this element of the covariance matrix only. And if we use this formula, we get exactly the same again, minus 3.9%. So that is the solution we get. And of course, that formula is the formula, the closed form solution to get the weight of asset one. Once you have asset one, it's just one minus that gives you asset two. Okay, so this is using the formula for a weight star if for a two asset portfolio. Okay, and check, it works. And this was using solver. So bottom line, I have taken some time just to show that multiple approaches, and then this is matrix, lead us to the same place. So these are the weights. Okay, how much risk am I taking if I do go ahead and invest in this portfolio? 1.92 is your total risk or volatility for this portfolio. Okay, and then one important question, if we scroll down a little, we have another slide here that I oftentimes use in some activities. And then the lady wants to know, okay, what is the return I am getting from this specific portfolio? So here the data is not changing, it's the same, but now we have more information. We have the returns. Bonds are giving us an expected return of 4%. Equity, we have an expected return of 8.5%. So let's have this here, 4% for, I'm sorry, 8.5% for equity and then 4% for bonds. Okay, 8.5 per equity, 4% per bonds. Now, what is the return? So we can easily calculate the return here. Okay, let me just copy this. Let's say return of portfolio optimal portfolio. Okay, and now we can use matrix form to get this, and the formula would be M mult of transpose of W, comma, ret. I have not named it. Let me name it. This matrix now is the return matrix. I'm going to name it ret. So it would be M mult of transpose W, comma, ret. Okay, that is the matrix formula for this specific to get the return of the portfolio. Okay, now it would be 3.82% for this portfolio. So the lower the risk, then we are also ending up with a lower expected return. Of course, keep in mind this is an expectation. So realized returns could end up being lower than this. There is no guarantee that you are going to attain a 3.82% because this portfolio has risk. 1.92 is the measure of its standard deviation. Now, I used, and I can do this formula text, matrix form here. Here, and you can keep that formula. It comes in quite handy in many opportunities. But you could also, the specific case of returns, this is just a weighted average. So it's much simpler than the variance because we don't have any other um, relationships like in variance. We also need to account for the covariances between each one of the assets, right? Like there are some, if you're investing in gold and you're investing in equity, when equity goes up, when equity goes down, oftentimes then gold will go up. So we need to account for those. For that reason, variance is much more complicated. Here we have a matrix formula. But this matrix formula is simply the same as sum product. So for the return of a portfolio, it's actually much simpler. Sum product of W and red, that is the same. Okay, so I invested 103.9 in this asset, so I'm getting a 4% out of this. And then I shorted 3.9 on this, so I'm multiplying what I invested by the 8.5, and then I add up how much I got from asset one, how much I got from asset two. Okay, now we are calling, and with that I conclude, we are calling this optimal portfolio. Okay, there is not such a thing as we cannot call this an optimal. This it doesn't mean if you are starting, you're excited, you want to start investing, and you want to start investing in risky assets. This is the best portfolio for you. Okay, now we have a specific goal in this specific case, and that is this elderly lady wishes to minimize risk. So her goal is to minimize risk. Now, in if that is your goal, then this is the portfolio that leads you to the minimum, to the lowest possible risk. So if this is the only goal that this lady is pursuing, this would be the best portfolio she could adopt, which is the one where she has the that she's reaching the best possible value, lowest possible value for variance, which is the metric that she's paying attention to. In real life, we're going to see in other problems. Then, of course, you have some other constraints like, okay, but I want to minimize risk. I don't, I want to have as little risk as possible, but I want to achieve an expected return of 10% or 15% or 8%. Okay, that is another layer of complexity, and we are going to see videos on that. In the meantime, this is how we get the optimal weight for minimum variance portfolio. Thank you for your attention, and let's keep in touch.